All right, let me walk through a really quick Bayesian updating example. This is, if nothing else, for the benefit of just loading Bayes back into my brain. So, looking at the question of what are the odds of any particular outcome in liar's dice? That is our motivation here. So the dice that we're going to roll, we're going to get using sample. So here I'm assuming we got 3 players and each player has 3 dice. So capital L is going to count for 15, representing the number of dice we've got. So we've got a particular roll of the dice. Now, the idea is that each player can only see their 5 dice. So let's say my private data is that I see these first, the first, this is the first row. So the dice have been put into a matrix, and I've taken the first row of that matrix and said one of the players can see that. Let's think about how that player is going to update their probabilities. So what sort of probabilities are they going to be thinking about? They're going to be thinking about things like there are n number of some face value on the table, period. So in this case, we can actually look at the outcomes, and if I were to take this project a little bit further, I could then put in a way to not just ask what's the probability that something happens, but see, did it actually happen? But the more interesting part is the probability, because that lets you automate a player's behavior so that you could simulate a game of liar's dice. So in this case, there are 3 threes. But I could ask the question, what is the probability that there are 5 threes, given that I'm this player and I see that I've got 2 threes? 5 threes shouldn't be a bad bet if you know there are 15 dice and you know that 2 of 5 of them are already equal to 3. All right, so how are we going to get this? So I'm going to start with a really lazy way to get some prior probabilities. So I'm just simulating, what, 1,000,000 times. 1,000,000 of these, and really I should make this L instead of 15, just so that I could change that up further in the script. So I've got T, I've got counts, and what do my counts look like? Those are my counts. So this is the number of these sample rolls where there were a certain number of ones. So I'm just choosing one arbitrarily. I'm saying we roll the dice 15 times with replacement, and we ask, what is the sum of those 15 dice that is equal to 1? Okay, let me just walk through that code one more time. Equals 1. Right, so that was out of a random sample. Right, so out of here, I could take this. I'm getting something like that, and then I'm asking, where do they equal 1? Right, so this is a different sample, but we got a 1 up front again. We get a 1 in the middle. Here we got 2 1s in the middle. But then we're just adding that up here. Right, so T is going to be a big, giant thing. 1,000,000 elements. But this is just, we got 2 1s, we got 5 1s, we got 2 1s, we got 1 1, and so on. Let's just see the first 25. So sometimes we get 0, sometimes we get 6. Cool. So that is our counts. And what we're doing here is we're counting up how many happen from 1 to L times. So here's the number of 1 1s, 2 1s, 3 1s. 0 of the million times did we get 15 1s. We could have gotten that, and strictly speaking, there is some probability we could get to that with a higher number of simulations, but that would just take longer. It would be more accurate. Of course, even more accurate than that would be to do the actual math on this, which I think actually, in the case of 15, it's going to be what? You're going to have 1 over 6 to the power of 15, which is going to be a teeny tiny number anyways. But in any case, while I was working this out over the past couple days, that's what came to mind, so I'll stick with that, right? Don't need to reinvent the wheel. This is good enough. All right, so then my priors, I'm going to take those counts and I'm just going to repeat them. So there's my counts, here's my priors. The probability of 1 or 2 or 3 or 4 or 5 or 6, they're all the same before I've seen any data. Now I have actually seen some data, but I'm setting up for the probabilities to be updated when I do see that data. All right, now this is basically telling me that for each row, I'm sort of implicitly saying there's 1,000,000 observations we've done. Right? And I can see if I do priors, pipe that into row sums, I think I'm going to get a little less than 1,000,000, right? Because I'm not counting the zeros. So strictly speaking, I should include the zeros. And I got a little note in here that this would be easier if R indexed from 0, right? If this was column 0 instead of column 1, and this was row 0 instead of row 1, we'd go from 0 to 5, which would be a little bit annoying here. But in the columns, it'd be nice, right? Because then we could really easily add in that 0 and say, we want to think about the conjecture where there's 2 3s as column 2, row 3, but whatever, right? Well, we're just going to ignore those zeros. That's technically making this work a little less accurate, but whatever, right? As long as it's inaccurate in a consistent way, we should still move in the right direction, right? We've already got this thing where 3 of them is more likely than 1 of them, which feels better, right? If we're rolling 15 dice, rolling 1, 2 seems at least a little less likely than rolling 3 2s. So I'm happy enough with where it is. If you really wanted to make sure you're going to do a good job at winning at Liar's Dice, then you take this and you fix it after you get the other stuff working. My focus is getting the other stuff working, not having it perfect right at the bat. So what I'm going to be asking is when I look at my private data, I'm going to ask how many ways could I get that data if certain conjectures were true. So how could I get, let's say, out of the dice, let's see, out of the outcomes. So we've got 6 5s. How many ways could you roll 15 dice and get 6 5s? I'm going to use this nChooseK function. I'm going to say out of 15, choose 5. There are 3,003 ways to do that. Now, how many ways are there to roll 15 dice? That's going to be what, 15 factorial? Which is a huge number, right? So 5 out of 6, 5 dice, 5 6s out of 15 dice is a pretty rare occurrence, but there are ways that this could happen, right? So this basically means maybe the first one is a 6, maybe the first 5 are all 6s and the rest are not. Maybe the first one is a 6 and the last 4 are 6s and the rest are not. Right? There's a number of ways that we could choose K out of 15 elements. All right, so we're going to use that function to write this function, ways to get. So we're going to ask how many ways to get. Well, we're going to get some face value, right? So say 6. We're going to have some observation, say our private data, some conjecture, which is going to be there are exactly 5 6s, right? So what's the probability that we would see this, or how many ways could we we're assuming that there are exactly 5 6s, which there are in this particular sample. How many ways can we get what we observe is really what this all boils down to. So we're going to ask, how many of the face value do I have? So again, let's look at private data. So I'm going to look at 3s because I got 2 3s, and I want to see what happens when I run this through and ask how many ways could there be 2 3s if there are in fact 1 3 in our 15. So ways to get, we're going to look at 3s. Our observation is our private data. Our conjecture is 1 3. And our dice on the table is L. I've set that to a default value of L. And this spits out 3. So what if there were 2 3s? Well, there's 10 ways that we could get that. 3 3s, there's 100 ways we could get this data. There were 15 3s, there's no ways I could get this data because not all of my data are 3s. Let's see, if I go 13, still 0, 12, I get some possibilities. Right? So it's possible that I have 2 3s and the other 2 players all have all 3s. How many ways could we get that? There are 10 ways. Well, 10 out of a million is not huge, but it is at least somewhat consistent with the data that I can see. All right, so let's see how this is working. I'm setting the private count. How many of my observation have this face value? Let's sum those up. That is my private count. So my private count would be 2 when we're looking at these 3s. The public count is the conjecture. So if I say there are 12 of these, let's say 13. I say there are 13 3s, and I say 13 minus the 2 that I have means that there are 11 out there in the public count. Now the public count, in this case, is greater than 15 minus the 5 that I've got, so that's impossible. So I'm going to return a 0. Likewise, when I did this for 1, my private count exceeds the conjecture, so I've disproven that there is exactly 1 3. So there are 0 ways to get 2 3s out of 1 3, so I return 0. So if I get either of those special conditions, I return 0. Otherwise, I'm going to do this thing. This is a little bit of a mess. Let's see, and I don't need this. So n choose k, the length of the observation and the private count times n choose k, everyone else's dice and the public count. So I'm asking how many ways could I get those 2 3s, these 2 3s out of my 5 dice, compared to however many dice must be left over. How many ways could we get those out of the 10 dice otherwise on the table? And I tried some different numbers here, right? So this is kind of lazy unit testing. I'm just setting up something where I know something should happen, right? So when I plug this in with null data, no observation, it's still giving me something. That's good. In that case, it's what, telling me out of 5 choose, or out of 15 choose 5. Cool. So out of those 15 observations, looking at the 5 column, or a face value of 5, how many ways could we get, how many ways could we observe nothing if there were 5 5s? Well, nothing means that we haven't eliminated some of these special cases, so it's just going to give us the raw count of how many ways you could get this. All right, so all of this is counts. And the nice thing here is that we can use these counts. We just have to multiply each time to update. So each time we observe new data, we can take our priors, which as of right now, we haven't updated, and we can say, all right, given our private data, how do we modify this? Well, for example, this should go to 0. Likewise, these are already 0, but let's say that they were just a very small number. So for, let's say, 6, well, we couldn't have 15 sixes, 14, 13, 12. We could possibly have 11 sixes, right? So if these weren't already 0, we would want these to become 0. Likewise for 4. For 1, this should become 0 also. So I just set this up in kind of a lazy nested for loop. So I'm going to loop over each row. So I'm going to say for each row, let's go for each column from 1 to 15. And again, we're ignoring the possibility of zeros, which is being a little bit sloppy, but it's going to be good enough. So we take our prior, which is just, some element, and we create some update, which is just counting what are the ways to get what we have in our private data given what we see, right? Or sorry, given the conjecture, right? So given the conjecture, what's the probability of being here? And then we're just going to multiply this number by the ways to get that, right? So the ways to get that, what we're going to see is, let's kind of focus on row 3. Let's go ahead and actually just run this. And then we'll look at priors row 3. So that 1 became a 0 because, well, the ways to get 1, there was 0. So 0 times that, we get 0. Given our data, we have eliminated that possibility, right? There cannot be 1 0. There could be 1 or more zeros, right? But there cannot be exactly 1 zeros. So here was priors before. Let's scooch this just so we can see. The numbers are all the same. So 273, this got multiplied by 10. This got multiplied. A lot of these numbers got a lot bigger. This 3 looks like got multiplied by 100. So now we've got out of how many ways? Out of a bajillion ways. We've got different counts of different ways to get some number of 3s, or to get, rather, the simulations we saw, which is just prior probabilities. We've updated those prior probabilities to account for our private information. And then with that, all we do is, this is called a softmax. We can take priors 3, and we can divide it by the sum of priors 3. And this is going to convert this all into something we can think of as probabilities. So this is useful for actually acting on this data, but this data is going to be a little bit easier to update because as you get new data, right? So you could say, my opponent made a bet that there are 3 4s. Okay, given what I know, how likely does that seem? Right? That would be looking at these probabilities, but then also, given that they made that, how do I update? Well, I haven't figured that out in this script, but that is certainly something you would want to do, right? So certainly if you're, say, playing poker, you want to be doing the same basic mechanics. You want to say, what are the odds that I get this? And then what are the odds my opponent makes that bet, given what I know, and given what I know, and given what they did, and given what I know about them, what should I do to update my priors at that point? Now that part is much trickier. But in any case, I have wrapped this up into one little function, but more importantly, I've gone through the basic logic, and that basic logic says we take our data and we update our probabilities to account for that. And I've made at least one mistake, excluding the 0, but that, not a big mistake. I might have made a bigger mistake, but I'm pretty sure I've got it here. If I haven't, let me know. So hopefully this is useful for those of you who have a Bayesian element in your project.